Yes, sorry. Should be good now. Okay, you see my screen?
Yeah.
Okay.
Okay. So hi everyone. We are group one, and we are talking about finding relation between character in a movie script. So for the summary, we'll present you the project objectives after our Scopper implementation about EMSDB, relationship between character and analysis, and user-friendly web interface. For the project objectives, our primary goal is to develop a system that can automatically retrieve and analyze the relationship between characters in a movie script using natural language processing techniques. This will involve identifying and categorizing the interactions and connections between characters, thereby providing valuable insight into the narrative structure and character dynamics.
So the EMSDB scraper implementation. So each script file contains structured data with details such as the script title, the authors, and dialogue categorized by actors. The script information is organized in a dictionary format before being written into a JSON file, ensuring that each script is stored with clear label for its title, authors, and the dialogue associated with each actor. So this is a output example, a JSON file from one of the scripts. So we can see the actor name, the dialogue, and information about the movie, title and authors. So this is the diagram for the relationship between character analysis. So we have different function. So there is the aggregate conversation, which takes the script data and the main characters as parameters and returns the aggregated conversation, as we just saw before. Then the classify relationship, which takes the conversation and the relationship classifier and the emotion classifier, which is two different model. Um, then they return the relationship classification. And finally, last function that use the emotion model, which will return the emotion between the two characters. So we use the web database for question answering. So the purpose is to answer the question based on our provided context. So the training dataset is the squad 2, which includes question with no answer. Uh, so we give the dialogue between the both characters as context for the model. And this is a schema of the overall performance with answer and without answers. So for the relationship between character analysis, so we ask a question to the model, what is the emotional bound between X and Y, and the context is the aggregate conversation of the both character. So you can see a simple script of our project. The second model is the Roberta. The purpose to classify emotion in text with the multiple possible labels. So go emotion based on already data with 28 different emotion labels. Each piece of text can have more than one label. Precision, this means that the model got the answer exactly right. So around 55%. And recall how many of the answers given were correct versus how many of the correct answers were found. And F1 score the model accuracy in understanding context and providing relevant answer, which is around 60. So again, the same schema. And this is an output example for the Titanic movie with the pair of actor Rose and Jack. The relation is I love you, Jack, with top emotion love at 93%. And after this, there is all the aggregated dialogue. So we created a user-friendly web interface using Next.js, which allowed to select a movie from the list of available movies. Dynamic URL to know more about the movie using the moviedb.org website, and an action button to send a request to the Flash server and get the relationship answer. Just below, we get the list of relationship between the different characters with the aggregated dialogue, the top emotions, the characters, and the relationship. We can see an example of relationship between Lisa and Paul there, with relationship, deep passionate feeling for you, Paul, top emotion being caring and love. And we can see behind, just under the aggregated dialogue. So, the demo. So, for example, if we take the movie Titanic and we find the relationship, we can see that we get, for example, between Jack and Rose, the love at 95%. We can see the aggregated dialogue from the original script between the two actors. We can also see different relations between Jack and Ruth, devastated, sadness at 88%. We can try with different movies, such as uh, Avengers, for example. For example, between Emma and Peter, the love, between Mother and Steve, jealousy, with Happy Family, with the joy mainly. So, yes. And if you want, we can get information about the movie right there. Okay, that's it. Thank you for listening. If you have any question. Yes. I just show a live demo on the website right there. So I will do it again. So this is the example result for the Titanic movie with the different characters, the relationship, and the top emotion, and all the aggregated dialogue.
Okay, hello, can you hear me? Up, and here's my. Okay. So, hello everyone. Today I'm going to present our natural language processing and information retrieval project. So, in this presentation, I'm going to explain what subject we chose, who's our team, what strategy we used to solve the problem, and how we made the evaluation of our system. So I'm Jeremy Calvo, and I made this project with Alexandre Toural, Tony Bano, and Joël Joca. So we chose subject 3, which was how to retrieve a list of movies with a given query, like for example, searching love and find movie 1, 2, etc., by searching only the movie scripts dataset from imsgb.com. So for this project, I'm going to explain how and what dataset we used, how we formatted the data, then how we upgraded the user request, and finally how we made the search functionality. So in this project, we had to use the dataset from IMSDB. We chose to use the whole dataset and have every movie that was on the website. So the data retrieved was 1,147 movies and script. We also had every movie's cover image. For this part, we'd like to thank Group 7 who provided the whole dataset for the class and who made us gain time for the most important part of the project without having to do scrapping. So using the dataset, we had to format the data. So this means we cleaned the script to remove every unnecessary character, all the HTML tags from the website, and also the punctuation. So this means at the end, we only had the script text and the characters' names. So we could split all the script text into tokens. So now this is the research part. So as we wanted at the beginning, we could have a pretty simple research algorithm, but as it had been said, it was lacking originality. So we were wondering what we could do to improve this. And instead of making our algorithm better, we had the idea to improve the user request and the user query. So what we are doing is that we are using semantic tools to find keywords that are related to the subjects. So that could be synonyms, similar words, or even opposites. Why opposites? Because maybe if we want to look for movies that are talking about marriage, we should also look for divorce in the scripts because these terms are related, and a movie about marriage can talk about divorce. So to do that, we want to expand the user query with our own keywords. So to do that, we used a pre-trained model called GLOVE, which means global vectors for word representations. So as we can see in the example, if we are looking for the word uncle, it could be related to an aunt or maybe to a niece, to a nephew. If we are looking even further, it can be linked to woman or man. So we chose to use the GLOVE 6B model, which has a 400,000 words vocabulary. So this was a pretty big model, and it's going to help us, as you will see in the demo, to find related keywords to the query. So then when we upgraded the query, we can process it with the dataset. So what we are doing is we are looking for occurrences of every thematic that our query has, and we are increasing a score depending on the occurrences in the script. Concerning the evaluation, we made a manual test, like we made 40 tests to evaluate our system. What we did, for every query, we were taking the top 10 results and we attributed a grade to every movie. So we attributed 0 if it was irrelevant to the request, 5 if it has some points that were relevant, and 10 if it was totally consistent. So what we had for our result was an average of 5.45 score. So as you can see for some examples, but to do so, I'm going to show you our demo. So we made a web interface to make it more user-friendly and more easy to comprehend. So it's going to be clear now with the demo. So you can see my last week request, which was superheroes. So as you can see here, system found some related thematics because a movie about superheroes is also a movie about supervillains. It can also talk about zombies or mutants. And you can see here the top 10 movies that were retrieved. So we can have this is a pretty good example because these are movies about superheroes. And as we said, we had the movie covers, but I can do a new live request. So if I want to find a movie that's talking about dinosaurs, I guess the related keywords could be fossils or anything that has a prehistorical link. So it's going to take approximately 10 seconds. Okay, so we can see that the keywords, the expected keywords are skeleton, dinosaurs, fossilized, fossil, dinosaur, mammal, etc. So the top three movie retrieved are Jurassic Park, The Relic, and Jurassic Park: The Lost World, which are clearly related to dinosaurs. But we can also find interesting examples from our system. Like, for example, King Kong. King Kong is talking about a monkey, but it's a prehistorical monkey. So that's kind of relevant and that's interesting. Like, the movie is not talking about dinosaurs, but it will still retrieve because it has a link. So that's interesting. Or, for example, Godzilla, who's not really a dinosaurs, but more like a monster, but it is also related. So that interesting to see that it was retrieved. So this is all for our presentation. Do you have any questions? Thank you. Okay, so for the evaluation part, let me. Okay, so what we did is we split it in the group. So everyone in the group had to do requests, and what we did is we made our own evaluation system and criteria to understand what was relevant and what was not, and we chose to put scores to every request movie. So if I take my last example, for the thematic dinosaur, Jurassic Park will clearly be a 10 in our evaluation process. And then we made the average for every evaluation we made.
Do you see the screen? Do you see the screen? Hello? Oh. So we are team three, and then I'm gonna give you this presentation of our application that can query movie script with the fuzzy search. You may have an experience that some code of movie pops up out of your brain, but it's really hard to remember what the movie was, and even the code was not really precise that make you hesitate to type in the Google search bar. Then our application comes into play. So without a complete or precise sentence, you can find what you were searching for. So here are the key features of our system. First, you can search the complete sentence and the movie info with the user given incomplete sentence. And second, regardless of white space in the given query, it works really fine. And third, it displays the result with thumbnails from IMSTV poster if it's available. And we have additional features, the synonym search, which allows you to give to the synonym to the engine. So this is really useful given that we often confuse some words and this leads to a wrong Googling keywords. Now let me explain how we implemented this system. We collected the raw data into the HTML format from IMSDB, and we used the Lucene engine for the searching and Java Swing for the GUI. This is the bird view of our system. So we have the GUI for the user, and when the user gives the query to the system, the given sentence is parsed by the query parser to meaningful Lucene object here. And the query parser has a synonym analyzer inside of itself so that branches another query at the same time. And this queries goes to the search engine, which holds the Lucene movie script index, retrieves the result from there, and finally shows the output through the GUI. So the search engine has the search mechanism inside of the Lucene index, and index means the like inside DB that holds the Lucene data. The data for the Lucene index to be filled with the preprocessed from another Python script that stores the movie's metadata and each line of the script to the standalone SQLite file. With this file, the index writer joins the metadata table and script table to feed the Lucene index. Okay, so the metadata table contains the title, authors, and journals inside of this table. So this are the result of the pre-process steps from this Python script. And similarly, we have the script table holds the movie ID as a foreign key referencing the metadata and the character and the dialog table. These are the rule-based regular expressions to parse every single line and the metadata of the IMS HTML file. So by iterating these algorithm, we could parse like all the text from the every given sentences and the movie data. Okay, so for the search engine, we use the Apache solution as mentioned. It is really a powerful tool that supports high-performance full-text indexing with a lot of additional customizable features to improve the query system. The records of the SQLite file should turn into the Lucene index for the query engine. So this is a pre-processed step that we can run asynchronously so that we separate to another binary to feed this Lucene index. So we could find that every rows from the SQLite file converts into Lucene index file. And we can pass the analyzer layer with a filter that can handle white space or synonym. Especially for the synonym, with not only the built-in maps, we can give aliasing with extra CSV file. And to leverage the Lucene engine, the given user input should convert it into Lucene object. So these are the code that converts the given words to the Lucene query object. And the Lucene engine replies with scores of each element of the result called document. And then we convert this data to search response to draw the GUI. And so finally, we could achieve 100% of aliasing this what's going on and some wrong words with what's, but it's just really fine because of the default search that enabled by the Lucene. So let me show the demo real quick. This is the GUI of our system. When we search like what's going on like this, then we can get some movie posters and the scripts, the line sentence itself with the index of the script of the movie. And if you see the result, then it really gets all these tokens inside of the movie's title. So here's what's going on and what's going on here and blah, blah, blah. And even it is not really precise, then it holds the contents of here. Yeah. And as you see on the demo, it is not really precise then, but it could retrieve the data. And also we can give some alias here. So if someone confuse the force and the energy, and the user wants to query some sentence from the Star Wars, and maybe you have heard about some force may the force be with you, and someone queries like energy with you, then there's an alias that force and energy. So every scripts of the Star Wars are retrievable is fine, like this. And also, we can query with the correct sentence. Yes. So this is our demo. So thank you for watching. Oh, sorry. Sorry. Okay. Like for this presentation, we didn't made some recall for this presentation, but the Lucene engine itself guarantees the precision inside. So whenever we increase some another words for this sentence, it works really just as fine. And we added some like CSV alias. So if you want to improve our system, then you can add some another words to give another alias. Yeah, when we put what's going on here, actually this precision is really like only based on this query. So it may differ when we put another words to here, but for the presentation, we only like prepare this keyword. So maybe with another keyword, it might not really 100% precision. Yes. Yes, that's right. Thanks a lot.
Yes, hello. I will share the screen.
Okay, perfect. Hey everybody, my name is Eli and I'll be starting the presentation for our team today. So my teammates and I are exchange students, like many of you guys. We've spent the past semester of our lives living in and immersing ourselves in a new culture, in a new environment. We have had the incredible opportunity the past year to become friends with people from all over the world. And one of the biggest things that I've learned from this is how upbringing and cultural differences can influence and mold our worldviews and opinions on various topics. In the world, differing worldviews and viewpoints on polarizing topics can often be traced to the fundamental cultural differences between people and nations. Dr. Laurie DeLale O'Connor, expert in fostering equity in educational spaces, believes that culture is such a powerful influence on our outlooks and behaviors that often we're not even aware of it. And such unexamined beliefs can often lead to unavoidable conflict. Now, gaining an understanding of how others or our cultural upbringing influences our worldviews used to take a heavy investment of time and energy. And although technology will never be a replacement for this, because like you guys know, it's an amazing opportunity to really take the time to get to know people from different backgrounds and see how their upbringing, their culture shapes who they are, like who they are, their worldview. So that aside, technology does offer us the ability to get an overview, a snapshot, an idea of how someone's culture influences their opinions on a specific topic. So going down this vein, we wanted to be able to understand how different countries and cultures view different polarizing topics. Now, one of these topics on which there are a lot of differing opinions is LGBTQ rights. Acceptance of the LGBTQ community varies across the world. In an attempt to understand how attitudes towards the LGBTQ community differ across cultures and nations, our team built a program that analyzes the tone and meaning of LGBTQ-related YouTube videos and comments from a selection of countries across the world. It aims to be able to determine how the average person from a given region views LGBTQ rights. So how did we do this? We first needed to collect our data. So we used the YouTube API to collect video transcripts and comments regarding same-sex marriage from several countries and then translated them into English using DeepL. After collecting the videos, we were then able to analyze them.
So our first idea to see if certain text or video or comments is for or against the LGBTQ cause was to use a vector space model and what we call the mean cosine similarity. So we viewed the comments and video transcripts that we get from the YouTube API as a vector of words, like in a query. So we can use a vector space model to get the cosine similarity. So first, we need to create a weighted matrix, and so we need data to create this matrix. So we use the .csv file called anti-LGBT cyberbullying. So it regroups thousands of comments that are against or for the LGBTQ causes. And so with that document, we created a weighted matrix using the TF-IDF method. And so we can create after a vector space model. So like in a regular ranked search, you insert a query and it will calculate the cosine similarity of this query with the vector space model. And then we selected the first 5 entries to get what we call the mean cosine similarity. So we get the average cosine similarity of these first 5 entries. And by only using comments that are against the LGBTQ cause, a high mean cosine similarity will indicate a strong opposition of the cause. And after some testing, we found out that if this mean cosine similarity is above 0.3, the text is likely to hold a strong or violent opinion of the LGBTQ cause. It is not 100% accurate, of course, because since it is a vector space model, it doesn't have the real it doesn't really understand the meaning of the word, so it's not an absolute measure. It's just an other indicator that that we can use in our study.
So to see how well our model performs, we decided to compare our results to the results from a well-established out-of-the-box model. And for that, we chose Vader, which is a rule-based sentiment or polarity score calculation model for social media style text, so it should be very suitable for rating YouTube comments. And Vader uses a predetermined lexicon with words and their respective polarity scores, which was constructed from results from over 90,000 human raters who attributed each word with a score from -4, which means a very negative sentiment, to 4, which means a very positive sentiment. And Vader also takes into account grammatical rules. That would be typing words in all caps, adding multiple exclamation points, adding words like very or not, and even adding emoticons. So we implemented Vader through the NLTK library, and it calculates how we did it is we calculate the sentiment score for each sentence in the text, because Vader is used for short sentences. And then we averaged the sum of all of the scores by the number of sentences in the text. And the sentiment analysis score ranges from -1, which means overly negative, to 1, overly positive. And the rule of thumb for categorizing text into negative, positive, and neutral is from a score from -1 to -0.05 means that text is negative. -0.05 to 0.05 is a neutral text, and from 0.05 to 1 is a positive text.
Okay, so now I'm going to show a quick demo before showing the results. So I will the program takes a bit of time because it needs to go over comments and transcript video. So I will not maybe run it for very long. So, but while it runs, I will explain a bit how it works. So the main program is divided in 3 main categories. The first one is the ID scraper to get videos ID that are relevant to our search in the YouTube API. So it will return a series of ID video that the transcript and comment can go over to get the transcript, so to get a text, the text from the video, and extract the comment of said video. And because some comments we are looking for like Korean, Japanese, or Norwegian videos, these comments may not be in English, so that's where we use DeepL to translate these comments. So we get this kind of JSON with the transcript video and the comment. And finally, we can use the sentiment analysis that is running right now, that is paired with the vector space, the mean cosine similarity, to get results. So, for example, right now it has finished with France video. I'm going to stop here because it's going to iterate over like 5 or 6 more countries. So I'm going to let Elijah to talk about more details in the result section. But in the end, we get a result.json, and with each country, the general sentiment, comment sentiment, cosine similarity for the transcript of the video, and in the cosine similarity for the comments. I'm going to switch to the presentation and let Elijah talk about testing and analysis.
Yeah, okay. So before we dive into the results of our testing, I want to talk about 2 issues that we had with when we were testing. So first of all, due to the character translation quota of DeepL, we were unable to obtain a massive amount of data. You have to switch to a paid subscription to be able to translate over a certain amount of characters. So that was one issue that we ran into. And then secondly, we were testing several different countries, and we found that Polish and Norwegian videos did not support video transcripts. So our analysis of those countries is based solely off of the comments on those videos. So with that in mind, let's first look at the cosine similarity results for our testing. In testing, we found that if a comment exceeded, like Sean was saying, we found that if a comment exceeded a score of 0.3 for cosine similarity, the comment or video was likely insulting or opposed to the LGBTQ community. But none of our videos, we can go to the next slide, none of our videos had crossed this threshold. So we knew that none of the data sets were overwhelmingly rude. So we sort of decided to base our main analysis off of the sentiment analysis because it provided some really interesting insights. We tested the accuracy of the system by comparing our results with reputable studies on the public sentiment towards the LGBTQ community. We found, if we go to the next slide, we found that although most of the countries matched those public surveys and studies, France and Norway's analyses were slightly incorrect. So let me explain here. As Nora was saying, if the score is above 0.05, it is going to be positive sentiment. If it's between 0.05 and negative 0.05, it's going to be neutral sentiment. And below 0.05, it's going to be negative sentiment. So you can see here that France, the comments indicate that France has a neutral sentiment. Now, this disagreed with studies because studies show that France, the general population of France, 85% of people from France are supportive of the LGBTQ community. So although France's sentiment was not negative, we would have expected it to be higher. And the same general thing can be said for Norway. Norway is known as one of the leading countries in Europe for supporting LGBTQ rights. So although Norway did show positive sentiment in their comments, we would have kind of expected it to be leading. We would have expected its positivity to be higher. But apart from those two countries, the other countries really did fall in line with what the public studies showed us. For example, Korea is one of the, in Korea, 38% of people are supportive of the LGBT community in surveys done. And that is below the other countries in our survey. So that matched what our sentiment analysis said. And again, Poland is one of the, it's traditionally more conservative on the issue of LGBTQ rights. And it is, again, lower than the other countries. Then you look at Germany and the US, and they're pretty high in their positive sentiment towards LGBTQ. And that is, again, represented, or it's corroborated in these studies that we looked at. So in conclusion, our testing and analysis indicate that with further refinement, our method for detecting multicultural worldviews holds great promise. Although the testing data for our algorithm was limited, with a larger volume of data and the integration of additional natural language processing tools, such as singular value decomposition, our system could accurately assess popular opinions of different regions. The ability to detect the worldviews of different cultures by analyzing YouTube videos, comments, and other social media marks a significant advancement in our capacity to understand the world. Historically, understanding cultural differences, such as a region's stance on LGBTQ rights, required extensive research projects that consumed considerable time and resources. But our new method offers a way to obtain fast and accurate insights into the worldviews of cultures around the globe. Thank you. The countries were sort of not selected at random, but we took what we knew of several different countries around the world, and we tried to choose a variety of countries that sort of spanned. So we tried to choose some countries that we thought would be conservative on LGBTQ rights, and some countries that would be more liberal on LGBTQ rights, and sort of several in between. We also, the goal for this project was multilingual cultural analysis. So we wanted to pull in countries of different languages. Could you please rephrase the question? What do you mean by clustering the countries? Are you saying like grouping countries, and like, so are you saying like clustering, noting that, say, Poland and Korea are both conservative? We did not necessarily look into that in our report, in our research.
Okay, welcome everyone. And this is Team KJU, and today we will present our present project on enhancing movie scripts search using vector space model and transformation model. Our presentation will be done by this sequence. And we selected the task of retrieving a list of movies based on a given query by searching the movie script database from IMSDB. This task is fascinating as it allows us to refine the vector space model we previously implemented and apply it to a new domain, which is movies. To achieve this, we focused on two primary approaches, which is first, we sought to enhance the vector space model for better performance in retrieving relevant scripts. And second, we aim to develop a sentence transformer, specifically an RNL model, to delve deeper into a contextual and nuanced meaning within the scripts. For our project, we collected the three types of datasets from IMSDB using Beautiful Soup for web scraping. First, first database is a movie detail metadata, and this dataset contains metadata for like each movie, such as title, genre, producer, and cast, but excludes the script content. This contextual information is crucial for enhancing the search and retrieval process. And second is a movie script, and this dataset pairs movie title with their corresponding scripts. It is the primary dataset for our query-based search. And the last dataset is a evaluation dataset, and this includes movie from three specific genre, which is romance, family, and science fiction. It is used to evaluate the performance of our search model by comparing the retrieved results with this evaluation sets. To analyze movie script efficiently, several pre-processing steps were performed. These steps are essential to enhance the quality of the text data and maximize the model performances. For the vector space model, we pre-process the data by removing extra white space and converting to uppercase, removing stop words. Also, we customized stop words and used Porter Stemmer library to do the stemming procedure, reducing the words to their roots form. For the case of sentence transformer model, we corrected spelling using speller and we removed stop words by using NLTK library. Also, we removed specific nouns by using spaCy and normalized the text and filter short text. Also, we removed the duplicated data, and finally, we added the label value for the fine-tuning process to the original data.
We initially designed the vector space model to search movie scripts. The vector space model set the script with the highest frequency of the search term as the reference script, computed TF-IDF values for all scripts, and calculated the cosine similarity between the reference script and each script. Scripts with cosine similarity scores higher than a threshold were output as search results. However, the results obtained from the vector space model were unsatisfactory. To address this issue, we employed the TF-IDF method, focusing specifically on keyword relevance within the documents. The first step involved initializing a TF-IDF vectorizer with specific vocabulary containing the keyword. Then, to align with the number of results from the vector space model, the top 250 scripts with the highest TF-IDF values were output as such results. The use of the TF-IDF methodology significantly improved the accuracy of our search results compared to the vector space model. However, there still appeared to be room for improvements as the results were not yet satisfactory, and scripts that did not contain the keyword were not included in the output. We used sentence transformer as a second method to generate dense vector representations for movie scripts, focusing on similarity measurement and classification. We use the pre-trained model with fine-tuning to improve performance. First, fine-tuning model and tokenizer initialization. We used Hugging Face's tokenizer and auto model to load and fine-tune the model with a cosine loss function. This ensures high cosine similarity between label query embeddings and script embeddings. Second, embedding generation. Movie scripts are tokenized and encoded. The transformer generates embeddings, and min pooling is applied to obtain fixed size sentence embeddings representing the entire script's content effectively. Third, similarity measurement. For a given query, the model computes its embedding and compares it with pre-computed script embeddings using cosine similarity. Scripts with a similarity score above 0.9962 are identified as similar. Additionally, the model and data were moved to the GPU to accelerate processing, essential for large datasets.
Okay, and now we will show you guys our program's demo video. And this is the main screen, and we use Kinter. And this is the option window. So you can choose VSM and transformer. And this is the search window of VSM. And when we search the word love, we can get a result of love. And you can scroll to see all results. And we got this list. And second of all, this is the search window, a sentence transformer. And when we search a keyword comedy, we can get a result for the query. Okay, and to evaluate our models, we use the evaluation data sets, and we measure the performance using precision, recall, and F1 score. This metric helped us to understand how well our models retrieve relevant scripts based on the given queries. Vector space model showed 0.45 of F1 score, higher in recall. We estimated that the length of the text and the given query mismatch might be the big problem. And for the sentence transformer, the output was like this in the presentation. We expected to make better results by oversampling the data for fine-tuning between other genre, but there was a lack of time issue. So in conclusion, by enhancing the VSM and developing a sentence transformer, we significantly improved the search capability for movie scripts. This project not only allowed us to apply advanced NLP techniques, but also highlighted the importance of understanding context and implicit meanings in literary works. So thank you for your attention. To explain more, we had like two problems in like pre-training the fine-tuning model, which was there was a imbalance in data sets of the genre, and second of all, uh, the labels were too much, but like there was a label for romance and science fiction and some family and so on. There was a lot of labels, but we we like um we improved a model by reducing the label, but as I told you, we didn't have much time to deal with a data oversampling. So yeah, that two reason might be the biggest thing in the different results between genres, I think.
Hello, everyone. Can you hear me?
Yes.
Okay, so we are group 6 and we will be presenting our project, which is task 3, and I will let Adili start.
Okay, so basically we will introduce the project, talk about data collection, our systems, evaluation, we will do the demo, and after the conclusion. So now I will introduce our project. So the evolution of information retrieval systems diversifies accessibility and analysis of textual data. And there is an interesting application in the entertainment field, which is analyzing movie scripts. So this is our problem: how to retrieve a list of movies with a given query by searching the movie script dataset from IMSDB. So it's important to define the retrieval objectives and input queries precisely because it is a wide topic and we didn't have a lot of time. So basically, our system allows queries based on genres and emotions, for example, melodramatic or funny. So this is the keyword of to use. And so in this report, we will focus on funny and energetic movies query for the evaluation. So I'll talk about data collection. So the data was obtained from IMSDB, so the database for scripts, and the data extraction was performed using custom scripts and Beautiful Soup for parsing HTML pages. So parsing and collecting data was made easy due to the simple and consistent layout of the database across all movie scripts, with easily recognizable scene, character, and text differentiation. So the data preprocessing was done to tailor the format to our project needs. So basically, removing extraneous information like transition details, camera angles, and director names. And the pre-processing was crucial for answering correct script formatting. So our dataset was structured with each column representing a different film, and the rows contained scenes from respective films. And at the end, we had a final dataset with only the film in the column and the whole script in one row. So now I let my team talk about our systems.
All right, so about the IR systems, the initial method for creating our IR system was to use the genre of the movies. We did this by using the CSV that was shared by our class material, so thank you for that. And this CSV contains multiple things, of which a few were the movie name and the genre of the movie. However, we ran into a few problems with this because great amount of the movies only had one specific genre and not multiple. So that was a little hard to work with. And the cosine similarity does not work well when we have only a few words, like 1 to 3 words. And the match was only returned if a query is its genre. So, for example, romance would give us a high cosine similarity, but like an emotion such as love would return a very low cosine similarity. The 3 IR systems that we used 3 different methods. One was a classical vector space model with cosine similarity. The second one was Google's word2vector. And the third one was an emotion analysis called TextBlob. And these all return different query results. And our aim was to see which of these were the best, which I can talk about in the evaluation. So first of all, how do we evaluate our different models? We have a very large data set, 1,032 movies, and it's difficult to determine our precision and recall since we talked about our queries sometimes being emotions. So we had no way of ranking all of these movies based on what emotions they pertain. So that made it very hard to determine our precision and also made it a little bit harder to work with recall. So what we try to do is measure the accuracy. So how do the movies which are returned match the emotions or genre that we try to work with in our query? So how we solve this is by checking every results of every query manually to see if the movies that we got matched our query emotion. So I'll explain the first one, the classic VSM with cosine similarity. Here you can see that we had 4 different queries with each 10 results. 10 of these results were repeated movies, especially between funny and energetic and sad and melodramatic. And if we can go to the next slide. We ranked all of these movies by hand, and we found that for the first query, funny and energetic, 3 of the movies were actually correct to our query. For the second one, sad and melodramatic, 8 of the 10 were actually correct to our query, so that's a lot more. Then for sad, sadly only 1 matched our query, one of the results, and for romantic it was 5 out of 10. So the most accurate out of this one would be sad and melodramatic for the classic vector space model.
Yes, and then we decided to analyze the same queries for using word2vec while processing our text. And we can see that compared to cosine similarity, the cosine similarity of word2vec, the results of similarity of word2vec is actually much, and only 8 of the 40 recommended movies were repeated. However, despite that, we can see from the query funny and energetic, 5 of the 10 movies were related to the query, and for sad and melodramatic, also 5 of the 10 movies were related. For sad, only 1 movie was related, and romantic 4 movies were related. So as you can see, the most accurate queries were both funny and energetic and sad and melodramatic. And then finally, we decided to do emotional or semantic analysis to see if there's a difference between them. And in this one, what's unique about it is actually no movie was repeated again. So every query gave us a unique movie. And however, it doesn't do well with a romantic movie. All of the movies we got with the query romantic actually had a similarity score of 0. And the order of the results were actually related to the polarity score of the script. So although there's no similarity, the script itself, the polarity score of it determined the ranking of our query. And the accuracy we calculated for the query funny and energetic was only 3 out of 10. Sad and melodramatic was 3 out of 10. Sad was also 3 out of 10, and none for romantic. So both funny and energetic and sad were the most accurate. And so because we can't, as mentioned earlier, we can't check the precision and recall of all of our movies, we decided to analyze based on the returns from the queries we got. So the average match query of cosine similarity was 42%, and the median of the matches was 4, and there was no mode. And the reason we wanted to calculate mode is to see that if a model just does well on a genre itself, on like a certain genre, or if it can do well on like multiple genres. So Word2Vec has an average match of 37.5% with a median match of 4.2%, and the mode of the matches is 5. And TextBlob has an average match of 22.5%. Median of the matches is 3%, and the mode of the match is 3%. So we can see from this, although cosine similarity has the most accuracy, we can see that was averages are affected by outliers, and sad and melodramatic had a really high match over genres in general. Without like given a random genre, where Tvec would be actually more accurate because it also sees the context and between the texts within a given window, because of the 4.2 median and mode of 5 matches. And because processing our text and model takes a long time, I recorded videos of each model as in the demo. So here is for cosine similarity. And it just goes on like this. So I'll continue with the other models. So this is Word2Vec. I'll now also continue on with TextBlob, the last model we used. So I'll stop right here because the rest is very similar. So in conclusion, although the accuracy isn't that high, that could be due to many reasons. And one of the reasons is because our text was processed scene by scene, including scene action and scene dialogue, and these two might be conflicting. For example, in Word2Vec, the results for Romantic was actually returned frozen, the Disney movie. However, although we can see that Romantic it has to do with love, which are similar together, but the love addressed in this movie has to do with familial love. So these semantics aren't really analyzed and are very important to process before returning a query. And also because movies can have multiple genres, as you can see in cosine similarity and Word2Vec. Same movies were returned multiple times. And yeah, and in the end, we hope that you enjoyed the project, and we are ready to receive any questions. And these are the references we have. Thank you. Yeah, so in TextBlob, we wanted to basically just we wanted to see like emotional or semantic analysis, and it just returned positive, neutral, or negative. And we just returned the similarity based on cosine similarity and the polarity of it. So it doesn't really do well in movies that are quite nuanced, such as romantic movies. However, in movies that are like stereotypically more straightforward, such as like action or sad, which typically just tend to have like genres that are very similar to each other, I wanted to see how it would return. So despite it having a very low cosine similarity, it actually was able to return, for example, let me just show the screen when it comes to TextBlob again. So in here, the queer romantic, it basically saw that Django Unchained had a more positive polarity score, so it returned it first. And we just wanted to see if that makes a difference or not, like using different methods. For example, cosine similarity, we just saw the cosine similarity, like between the two, the text vector and the query vector. But in Word2Vec, we actually wanted to see like how well it does if we actually process the text and saw the relation between the words together. And we didn't do that with TextBlob. We just took the semantic scores of it. Thank you.
Hello, let me share my screen. Okay. Okay, hello everyone. So I'm gonna present you our project movie lister for the topic movie script. So in the beginning of the project, we had to start by the scraping part. So we gathered data from EMSDB for like the HTML pages. We had some issues with the time it took, so we used the concurrent programming with a thread pool for to gather it quickly. So then we extracted the data and the data we wanted for our web interface. We also had to clean the data and save it into a CSV file. So we made two CSV files, one with the title, the release date, the rating, and the image for our interface, and another file with the movie script with the scripts because the file was quite huge, and we didn't want to have all the data in the same file. It was quite inconvenient, and this is the data we shared on the e-class. It's the same data. So after gathering the data, we started to process the user query on our web interface and to evaluate that query with the movie scripts. We started by gathering all the movie scripts into the CSV file and read that file, and we applied the vector model. So we compared the user query with all the movie scripts using vector model. We implemented vector model using sklearn and cosine similarity model. And for the tokenization part of the dataset, we used the NLLTK. And then we got a similarity score compared to the string the user inputs. And we sorted those movies according to the score. The inconvenience we had is that if the string wasn't long enough, So if we just input like few words, it's not relevant enough. The vector model doesn't return any similarity, so we have to use long strings. We had some difficulties related to execution time. So because of the huge size of the file, so it was like 200 megabytes, it took a lot of time to apply the tokenization and the vector model with cosine similarity. So, and since we were making like web interface, we had to answer in less than 15 seconds. So we started by using threading in the vector model. It reduced by a lot of time the time it took to apply the tokenization part and the part of calculating the cosine similarity. But it still took too much time. So our solution was, since the movie scripts was a static file and it will never change, we saved the word tokenization into a CSV. So the NLTK tokenization was saved into a CSV file, and we reduced by a lot of time the time it took for us to calculate the cosine similarity. I will show you a little demo of our project. So right now, this is what I tried like 10 minutes ago. So if I input Rudy and Jacob, it will give me the movie scripts where that string appears, and it gives me a similarity score. So I call like a script in my backend, and this is gonna give to my front end the similarity score. So I can use another script. So for example, if I scroll a little bit, I can take this one, for example. It takes a little bit of time, but like 10 seconds. And so when I start calculating, I save the score into another file. Okay, so my string doesn't appear a lot in the other movie scripts, since 20% is quite a low score. But here I show all the movies where it appears, and that's it. Thanks for listening. I don't know if you have any question. Evaluation issue. Our issue was because the file is really huge, so the tokenization part was taking a lot longer than we expected, because the file was like 200 megabytes. So the tokenization part was the longest process to get the cosine similarity. So our solution was to save the tokenization in a CSV file. So we don't have to always calculate the tokenization, since it's a static. The movie scripts are static and they don't change. So we can skip tokenization process when I input my query, because it's already calculated. Thanks for listening.
Okay, then we would continue with sharing. So, can you see the slides?
Yes.
Yeah, looks good. So we are group 8 and we have question 4. I think we are the only group who took question 4. So our topic is retrieving the most representative movie actors for a given query. And for example, if you search for love, for example, you want to get Scarlett Johansson at the top. And yeah, so that's our table of contents. And we first talk about the data collection. So that was the most important part. So we based our database on IMSDB. So we first got all available scripts from IMSDB. I think you all know this process. And then we had a table like this with the script link and the movie title. And then based on that, we scrapped all the movie scripts with beautiful soup. And then it looked like this. I'm not showing the complete script here, it's too long. But yeah, I think you saw this quite often now. And yeah, based on that, we had a problem. Like we had to extract the dialogue, and for that we use like lots of regex patterns and another functions like general movie script keywords to get rid of all the unnecessary stuff and just get the dialogues out of it. And so when we look at this script cutout here from 127 hours, we got this result, like only this dialogue text. And yeah, then the next problem was how do we map the role to the actor? So how do we know which actor is really speaking the dialogue text? And for that, we are using IMDb as an additional source. And yeah, we are using the Cinema Goa library. So we can just get all the IMDb data stuff. So what we are doing, as an example, like the movie I showed before, 127 hours, we just search for that on IMDb and take the first result. Like this is, we're doing that in code and not in the UI, but just that you see what we're doing. And then we got, like with this approach, we got over 1,000 movies in the database. And the next problem was to retrieve the cast of the movie. And yeah, this is also on IMDb. We can like just retrieve the cast with each role name. So you can see James Franco, for example, as the role Aaron Walston. And yeah, we saved it in the database. And like this, we got around 80,000 movie roles in our database and about 56,000 actors. Yeah. And we had the next problem, and this was how do we map the cast to like the role to the script. So you can see like on the right there's the script from IMSDB, and on the left there's the cast from IMDb, and we had to map this now. And yeah, for that we just used like Fuzzy Wuzzy. Maybe some of you know that. It's an like comparison tool. We just used when it's over 80% similar, then we map the cast to the dialogue text. So for example, Aaron on the right is yeah, it's just the name Aaron, but on the left you see Aaron Ralston. But because Aaron is in Aaron Ralston, it get mapped, and as a result we get something like this. The title, the actor, the role, and the like dialogue text. And yeah, this is basically all the mapping we're doing. And so we got 270,000 scripts in the database with this approach. And this is our database diagram, but I think it's not really necessary. Yeah.
Good, then will I continue with the classifying of the movie scripts. So originally we planned to implement just a token-based vector space model, but then we ran into one logical problem. because here's an example dialogue, for example, isn't the moonlight beautiful today, which is a metaphor for some romantic or love. And if the user query would be, romantic or love, then we would have no mapping to the dialogue, and therefore we couldn't retrieve the right actors. And to solve this problem, we decided to follow a different approach. And we used an AI classifying tool that classifies in text into different emotions category. The classifier we used is based on BERT. It's a language model from from Google researchers. And the model we used is specifically trained on emotion classification. With this, then we could classify the different scripts because we wanted to classify each actor, like how romantic or the love score for each actor and for the anger score. And here you can see an example for Ryan Gosling in the movie Fracture. So for example, his first script has a love score of 0.03 or an anger score of 0.15. And his second script has a surprise score of 0.0 and so on. Then we just calculate the average for all the dialects an actor has to get a vector for each actor per actor in the end. And then we also have to classify the query. And that's quite easy because we can just put in the query from the user into the classifying tool and we directly get the representative vector. But we also ran into a problem here because if a user only gives us one keyword, for example, just love, then the classification based on the tool is not really accurate. So we need to put in at least a few words as a query.
Yeah, so now we're coming to the implementation of the ER system. We use the vector space model for it. Yes, I think everybody knows until now what a vector space model is and how it works, but yeah, I'm going to explain it quickly. So yes, we can see here we have an every actor and query represented as a vector, as Patrick already explained. And all dimensions of the vector space model are our classification categories. As we can see here, the joy score, the love score, the sadness score. Yes. And then we're calculating after we calculated the vectors for an actor and for a query, we can use the cosine similarity to rank actors corresponding to the query. Yes. But here we had one interpretational problem, and this was the problem is that, for example, when an actor has only one script and only one line he's saying during this whole script, then he could have a really high classification. And yeah, we don't want this because, for example, if an actor played one role in a movie in the 1970s and he says "I love you," then our classification model would say to 97%, yeah, he's good, and this means this would also affect the cosine similarity. This means he would be ranked pretty high. But we don't want this. We defined our user need as rather famous and newer actors than yeah, old but 100% perfectly matching actors. This means we had to implement a fame coefficient. And we implement this fame coefficient based on how many roles and dialogues each actor has. Yes, and as we can see here, we defined the max fame coefficient as 3 and the min fame coefficient as 1. And then we just gave each actor an fame coefficient in linear decreasing manner. Yes. Yeah, and problems during the implementation. So as Tony already said, the mapping of the actors was the most difficult problem because we had two different data sets and sometimes the data sets weren't even complete. This means we had missing information. Then classifying the scripts. Yeah, we had to build somehow an average because as I told you before, when one actor is only saying one thing, that isn't really justifying him to rank him on the top. Then figuring out the right coefficients, but we are going to talk about this in the evaluation as well. And yeah, then the missing scripts. For example, Henry Calvin, we extracted him as an actor, but we couldn't find any scripts to him. So somehow we had also to like avoid such circumstances. Yes, then we come to the exposing of the functions. We're using fast API and UI, and we deployed it as well. So first, fast API, here we can see on the picture our API endpoints, our HTTP API endpoints for the search classification model. Yes. Then the user interface, we implemented a user interface with Next.js and Next.UI. In the demo, you're going to see this as well. And here's just a small picture. On top, we have our search query, our search bar where you can enter search query, and then the actors corresponding to the search query getting rendered. Yes. And we deployed it on Azure. If you're interested to test it out yourself, you can just enter this link. I would recommend you the UI link. Yes. We come to the demo.
Now we're coming to a quick demo. So I'm using the deployed Azure link here. You can try it yourself if you want. I already filled in a query. So I want to search for actors who are most related to action-filled drama. And I think it's taking some seconds, but yeah, this is our result here. So yeah, you can see all the actors here who are fitting the best, and you also can see the role in the film they're playing. So for example, Jack Warden played Juror 7 in 12 Angry Men, and you can like go through all the actors, and you even have a pagination here. And you also have when you go on the link here, you get like redirected to IMDb, and you can have a look on the actor again. And yeah, we are trying another one. So maybe romantic scenes, and then we're searching for that, and then you get yeah, different results, and like, this is the most fitting results in our cases. Yeah, this is the demo, and like here's the API. You can see it also, and yeah, but I think that's not really important. Yeah. So now we're coming to our evaluation.
Yes, then for the evaluation, we defined 6 queries we want to evaluate the model with. For example, or you can see them there. For example, query number 1 was romantic scenes, or query number 5 was saddest movie performances. Then we ran into another problem, building the ground truth, because we thought that ranking an actor to a query like romantic or love were really subjective. And to create a more objective ground truth, we decided to go search for online rankings. For example, the one you can see in the screenshot for like best comedy actors. And then we retrieved online rankings that matched our queries or were close enough to our queries, and took that as an optimal output and compared this to our model. Yes. And then, as Lucas already mentioned earlier, we had this fame coefficient, and one big problem was figuring out how high the rate of the fame coefficient were. So in this picture, you can see it with a fame coefficient of 5%. In the next slide, you see it with 15%. And as you can easily see, is that the fame coefficient increases, or I mean, the results are better. And around 15% is, in our case, what we find out is like the best value for this one. But overall, our results are not this good. Especially our F1 score is pretty low. But we think it's, for one, because we have 2 little scripts in our database. We are missing a lot of information, like Lucas mentioned already earlier. We were not able to find, for example, Henry Cavill in any scripts or any roles. And I think he's one of the actors you expect for like an action movie or something like this. Also, the mapping of the actors doesn't work to 100% in the, that's what Tony mentioned earlier. Like we also have the coefficient of 80% there, but it's also just testing out and figuring out what works, what's good, what's worse. And also we think that the 6 dimensions we get from our AI classification model are too little because I think our causal similarities between all the 6,000 actors are too similar with only six dimensions. And in general, the classifier we use is not especially trained on script data. So if we had more time for the project, we could have trained a model on our own scripts, and this would definitely increase better the results, but we didn't have the time for that. Good. And that's the end of our presentation. Thanks for listening. And do you have any questions? The fame coefficient. So basically, we have an SQL statement that just gives us the actors ranked on the different roles they have in our ER diagram. Or I think we can explain this the best with our ER diagram. One second.
Yeah.
Yeah, exactly. So we retrieve all the actors based on the amount of roles they have in a ranked order. So the actor number 1 has the most roles, and actor number 6,000 whatever has the least roles. And then we just have this coefficient of with the maximum value of 3 and minimum value of 1, and then we just provide the points in a linear decreasing order. And at the end, we calculate the overall score with the cosine similarity times 1 minus the fame percentage plus the fame coefficient times the fame percentage. And for example, in our case, the best percentage was 50%. So the cosine similarity would be multiplied with 85% plus the calculated fame coefficient times 15%. Does this answer your question? Yeah, we implemented this on our own, or we came up with this idea because our results were pretty poor in the beginning, and then we figured this out. Any other questions?
Is this a question? Oh.
No, can you maybe specify a little bit more?
Yeah. I think I know what you mean, but we didn't consider that. Like differentiate between the protagonist and an antagonist. We're just focusing on the text the role is saying in the script. Yeah. Okay.
Hello, can you hear me? So I'm just gonna share my screen. Can you see? Okay. So hello everyone. Today I'm gonna present you our project that consists of retrieving a list of a movie with a given query from a movie script dataset from the imsdb.com. So the problem was identifying a movie. sorry. So like I said, we needed to retrieve a list of movie from a given query, and to solve this problem, we decided to use a vector space model. So I'm gonna explain it again, even if I suppose everybody know what a vector space model is now. So a vector space model uses vectors to no, sorry, to represent textual data as vector in a multi-dimensional space, where each dimension corresponds to a unique term from the corpus, and the representation in each dimension is uh, sorry, excuse me, I'm just gonna do it again. I'm a bit sick. So we choose to use the vector space model because it's useful in our case because we have a large amount of data. Like other group says, we have like over 200 megabytes of data. So it's really useful in this case. And we can represent textual data as vector, like we say in a multi-dimensional space, with each dimension represent a specific field. And we use the cosine similar data to represent all of these vectors. So we so we in our program we use a query with we're gonna see with the demo later that we just ask prompts and the user can enter the prompts and it just return automatically a list of results um, from the data set. And and after this we can do a comparison and with the vectors, and it give us all the data we need. Like I said before, we can see from a few examples with love space the list that gave us, and all the film with a score that I said earlier. Like the score is between 0 and 1, and we have two models, the base VSM and the hybrid VSM. The base model is just using IMSDB, and the hybrid VSM is using ISMDB and the movie database rating score to improve the queries. So now for the evaluation, we have a lot of metrics. So all of these metrics are pretty talking by themselves, like the number of matching movie, the periods where the most of movie were, etc. So we can see this now. We have a graph to see like when the, for example, love movie were like most I'm sorry, I don't know how to say it, but when the movie came out, when the love movie came out, so we can see that, for example, George Lucas and Ethan Cohen are the most popular writers for the movie script, and the drama is the most popular genre because its query is love. And now for space, we can still see that George Lucas appear because, like Star Wars, it's in space, so that's obvious. And the drama thriller, same. And yeah. So just before that, I'm gonna do a quick demo. Okay. I'm just gonna reload it. So I'm gonna start the script with -r. That means we have the mixed hybrid model. That's like with the TMDB and the movie database rating, because there are much more data available. I'm just gonna show you an example of how we store the data. So we have the IMSDB opinion and ratings, the user rating. We can see the writers, genre, the date, title with the script itself, the comments, comments count and average rating, and we have the TMDB comments count and rating, same as ID. So we clean the data too. I'm gonna show the what is it like before. So as you can see, for example, in the script we have all of this, and we just clean it using by removing the stop words, lemmatizing the word. For example, I don't know if you can see it really well, but it's just putting a word like written, like for example, if it's written base, it's gonna transform in based, so all words show up as the same in the end. Okay, so now if I type love, like I said, we can see all of this, and for example, space, we have the same result and score. So in conclusion, our model is pretty effective by combining the SM and the movie database rating. And with the hybrid scoring is pretty efficient. And I think that's all. Do you have any question?
I'm sorry, what is your question about the evaluation? Sorry, for the evaluation, we use the metrics you can see here to improve our system and see if basically what we made was working. So for example, we check that the most common period was really relevant to a movie or a script which went out about the query or this kind of thing.
Okay. I'm sharing my screen. Okay. So I will present our project, which shows the subject how to retrieve a list of movies with a given query, for example, love in the database EMSDB. So I will present our project and the futures, how we did the data retrieval, the search engine, and the evaluation, and in the end, our interpretation of the results. So we are making a search engine to retrieve scripts containing a certain keyword. And in addition, we can narrow down the results to have a more accurate and personalized result by specifying genre, writer, or a date. For this, we did web scraping on the website. We use Request, Beautiful Soup, and Panda in order to access the website, to retrieve the data in the divs of the site, and Panda to store and organize the result in the CSV file. So the columns in the CSV file are title, writers, genre, script, script date, movie release date, and the script. Why did we get two dates? It's because when the script date or the movie release date is missing, we can take one of the two, so we can have we can have all the time a date to work with or filters. Then for the search engine, so we took the data from the CSV file, and we are doing a basic keyword search with a filtering mechanism based on the criteria of genre, writer, and date range. We can consider this model as a simplified Boolean retrieval model because it has exact match. It searches the words in the script and genre based on finding the exact word using the expression we give, and it has the AND operator. We can narrow down the results. So if we give a query for love, if we want more precise result, we can use the genre romance. If we want a specific writer, we can give it, and we can give a date range. So if we want the film before 2000, we precise the end date as 2000. In fact, we retrieve more genres than the IMSDB website itself, because some genre in the filter of the site are not listed. I will show that after. For the evaluation, we did an evaluation on recall precision and F1 score. We did a manual evaluation, sorry. For example, for the query love in the genre Western, we obtain 15 results with the search engine. And then on the 15 result, we manually check on the IMSDB website if they contain the word love, and it was the fact. They contain the word. So why are we getting high recall and precision rate? It's because we are only using a simple keyword search. So we get a precise result, and moreover, we use a filtering system to have more accurate result. What were the limitations in the project? It was that on the dataset, there were some missing fields, like some films didn't have writer or didn't have genre. So we didn't retrieve those results because it couldn't have work with our filtering system. It represents like less than 1% of the result. Then we have a simple, for the demo, we have a simple user interface using Python. So, okay. So here, if I search the word love, I will have a very long list of all movie containing in the script the word love. So if I want to narrow down the result, I can go with romance. And my list is significantly less, I have significantly less films. Then if I want from a certain writer, we have an autocomplete suggestion for the writer. So I will go with Tim Burton. And we can see we have Edward Scissorhands. And if I click on the title, we are redirected to the actual script of the movie. Then we can see in genre that, for example, here we have the genre sport that is not listed in the actual website. And if I search for it, I obtain 2 films. And if I go, we can see that he has the genre sport. So that's all for this presentation. Do you have any question? The chat is blank for me. Okay. Okay, we divide the work in 3 parts because we had the scrapping, the search engine, and the evaluation of the result. So Adrien did the scrapping, I did the search engine part, and Valentin did the evaluation and the interpretation of the results. Yeah, after evaluating, we saw a very high percentage of precision and recall, 100% all the time. And why we get this result is because we did a very simple, we use a very simple search model, Boolean model with only the operator and. And also what I forget to say is that when you use filter to narrow down the results, all the filters are used with the operator and. No problem. Thank you for listening.
Hello, can you hear me well? And can you see my screen? Okay. Okay, so I'm gonna talk about our team final projects. We choose the topic of the retrieve of a list movie with a given query on the given datasets. About the different steps of our process, we first scrap the dataset to get all the required film scripts. We use Beautiful Soup. Then we apply our query and we retrieve all the different movies with this query. For that, we have a web interface that I will show, and then we rank them based on the precision. So we can say like that film is more interesting than another. So for that, the script retrieval is from the given data sets. We have a backend that is the downloader, the searcher, and the if answer, and we have a front end to have a user interface to execute the query. So first, about the film download process. When we launch our backend, it downloads automatically all the scripts that are required. If these are not all here. So for that, we use Python Beautiful Soup. We can download absolutely all the films. And for the enhancement of our query, we also download the film styles. So first, you can use our web interface to enter query. And with the query, we will start the calculation and then show the results. But the most important part is that we implemented an advanced query system. And the goal of the system is to understand the meaning of parts of the film to like have a better rank and a more advanced search system. So for that, we use OpenAI to generate like same words like our query. And then we are applying different queries with all the words that we generated by AI. And at the end, we can cross the results of our different vectorial search to have films that have not only the query, but also the meaning behind this query. About the results, so both the search system and the vectorial and the meaning query are working. So we can have results like this with a score that is edited, that is like not only showed by the vectorial, but only like you have the crossed score. Here is a little demo of our system. We jump to the most important parts. So first you can like type a query here. Then it's searching. And up. At the end, you have the different results like this. I can show you a live demo if you want to search something after. And as an example, you can also like check the box here, and you will see that we have different results and here words generated to enhance the query. Thank you for your attention. I just let you give me question if you have question about like the cross vector system. I did not explain all the details because our vectorial implementation is the same as the first project, but we added the cross like to multiply the different scores if we have the meaning query checked. Thank you. Okay, yeah. About our evaluation, I will just jump on the scores. Here, as I say, it's like the same thing about the first project. We use the recall and the precision, and the recall and the precision on the first project were about 88% for the NR and 89.8, I think, with the vectorial search. So we use the vectorial search as the same project. The main difference is that because we have a very high precision with our first project, we use that system to create the better system to have the meaning understanding. And also to have the ranking, like as you can see as in our report, you will have the ranking like with that query. This film is more talking about love than another, for example. the web framework is it's React and TypeScript. It's like an advanced JavaScript. So you can just use that. It looks like that, and you have the video also in the reports and the code. Thank you.
Okay, hello, can you hear me? Yeah, we're next. Can you tell me if you can hear me correctly?
Yes, we hear you.
Okay, thank you. Okay, so we're gonna start. Okay, so hello, we are Nathan and Miguel, and we will present you, like you all did, our project for natural language processing and information retrieval. We chose topic 3, which is how to retrieve a list of movies given a query, and the retrieve movies will be in order of relevance. So we will talk about how we got the data with scraping techniques and the 3 models of information retrieval that we used. These are FSM, BM25, and a pre-trained BERT model. So we're gonna start with data scraping. Our goal when retrieving the data was ending up with a CSV file containing 2 fields, the title of the movie and the script. We use the IMDSB database provided to us by the professor for retrieving this data. And we use the library Beautiful Soup in Python. For retrieving this data, I'm going to show it better in the wait. I have the Zoom thing so I can hear it. First, we went to the URL that had all the scripts. Here it has all the movies, and we iterated through every title of the movie. Why the title? Why we did this? Because if we go into the URL, actually, you do request, you have to do another request, and the script URL for every movie consists of the base URL / scripts / the movie title, replacing white spaces with line. From this way, with only the movie titles, we could form the script URL directly without having to do a lot of requests, thus optimizing our code. Then we store this into a CSV, into our CSV file, and we got a total of around 1,200 different movies, since we scraped all the movies from the website. So now we're going to start with the VSM model, in which we used 3 different methods for calculating the weights. A VSM model represents text models as vectors, such as words or terms. So it can use different methods like bag of words, TF-IDF, and word embeddings, because they all transform text into numerical vectors, but in different ways. And it uses cosine similarity between vectors to retrieve the documents. First method we used in VSM was bag of words. Bag of words is a method for text representation where a document is converted into a vector, with each element representing the frequency of a word in the document. The good things is that it's simple, it's easy to understand and to implement, and it's efficient. It has fast computation. The not so good things, it's lacking on context. It ignores the order and semantic of words, and also ignores synonyms, which treats different words that have the same meaning as if they were completely unrelated words. So here's one evaluation we did. First, we have to say that we are evaluating our models based on the precision until k equals 30. This means we're calculating the precision until retrieving 30 documents. We think 30 is a reasonable k value since the normal user will not look at that many options, and it's good for seeing the position. Here are our results for a more specific query. Using the query space planets, we actually got an accuracy of 100%. This means that all the movies retrieved had a relationship with the query. In the case of precise queries like space planets, for verifying if a movie was correctly retrieved, we looked the plot of the movie online for every movie. You can see in the title it says it was made with an enhanced bag of words. This is because for all our models, well, for the bag of words and TF-IDF, we made two versions: a basic version and an enhanced one. The enhanced one has techniques for removing stop words, lemmatization techniques, and maybe we also try to implement diagrams. So now a little bit quick demonstration of our bag of words model. Here we can type any query we want. I already loaded the model, so we didn't have to wait. We can try space planets, which is the same query we did for evaluating. We can say how many results we want to see. Now it's gonna take a few seconds, 2 seconds or so, and here it retrieves in order of similarity all the results. We have Guardians of the Galaxy, Lost in Space, Bill's Milkshake. It looks kind of decent. We can do with other things, and it should work the same. Money Heist. You want to see a movie about Money Heist. You want to see 10 results. You wait again a couple seconds, and yeah, these are correct. Casino, 3 minutes or less. American Gangster. We have good results. So I am going to start executing the next script we will see. So it starts loading. It takes like 20 seconds, but like this, we don't lose any time. So, and now we're going to see, we will see the bag of words basic model versus the bag of words enhanced model. Here we compare the performance of both models. We did this using a very general query like love, because a lot of movies can talk about love, but not be romantic. And for evaluating this query, we looked at the genres of the movies retrieved, So the precision is probably higher, since the movie cannot be of a romance genre, but anyways, still talk about love. We did it with a general query like love, because if we used more specific queries like space planets, the accuracy was too high in both models to compare them correctly. So we kind of suffered from success. So anyways, with the general query, we can see that our enhanced model actually improved the precision. After retrieving 30 documents, the base model had a precision of 54.5%, and the enhanced model a precision of 81.5%, more than a 23% improvement. Moving on, we tried with TF-IDF, term frequency inverse document frequency. It's a method that reflects the importance of a word in a document relative to a collection of documents. In other words, it adjusts the frequency of a word by how commonly it appears across all documents. The good things, like it gives higher weight to words that are more informative and less common. So it reduces noise, because it reduces the impact of common words that are less informative. The not so good things is the complexity is more computationally intensive than bag of words, and it still lacks context. It still ignores word order and deeper semantics. Here we have the results for this model, calculating the weight for TF-IDF for the first 30K results. The maximum precision was achieved at K values from 3 to 9. After retrieving 9 movies, we had a precision of 100%, meaning all movies were related to the query. After 30 retrieved movies, so K equals 30, 28 retrieved movies were valid towards the query, which gives a final precision of 93.3% after retrieving 30 documents. Again, a quick demonstration. We could do space planets again. We can say how many we want to have Space Odyssey, Lost in Space, Space Milkshake. Yeah, they all look good. We could do, I don't know, zombies. improvising this to see some results. Yeah, Dawn of the Dead, Day of the Dead. I don't know the movies, but they sound kind of relatable. Paranormal, Resident Evil, Land of the Dead. So yeah, the model has good accuracy, especially when you give more specific queries. Again, we had a base version of the model and an enhanced version. We can see some upgrades too. We can see how the model starts with the same precision until k equals 2, but the enhanced model has a better performance for bigger k values, reaching a maximum precision of 86.7%, which is 13.4% more than the peak precision of the original model. Sorry. Then precision starts to decline. But we see this as something normal, as the more movies you retrieve in a the more movies you retrieve in a less time, the less movies there are in the data set related to the query when they're having more movies retrieved. So now moving to VSM with word embedding. Word embedding is a method of converting words into numerical vectors so that words with similar meanings, again, have similar representations. We used word embedding with word2vec, involves training a neural network on a large campus of text to produce dense vector representations of the words. It uses two main approaches, which is continuous bank of words. It predicts a target word based on its context, and also we have that it predicts the context words given given a target word, which is called skipgram. Like this, we can also try to capture semantic meaning. As before, the model starts well with a precision of 100%, but slowly the precision converges until having a final precision of 70% after retrieving the 30 documents. The best K value will be 12. So in other words, after retrieving 12 movies, we have a precision of 91.6%. With word embedding, we cannot do a live demonstration right now since Nathan is having problems with the environment just for this script, and my computer, oh, sorry, and my computer loads this model pretty slowly. So we can share screenshots we made before presenting. This happens because this is the only model from all of our models that after loading the model, the retrieving time for the movies, it's slower. So we can see the execution with the query space planets on the top left, and another execution we tried with the query money. We can see it has decent results, containing movies related to the topics such as Repo Man, Jackie Brown, Tin Man, Casino, among others. Now Nathan will share his screen and continue this presentation so he can show you other live demonstrations on his computers.
Yes, thank you, Miguel.
Well, I'm trying to.
Can you stop your share screen?
Oh, here. Sorry.
Okay, so let's move on to the best matching 25. Wait, sorry, I'm having problems. Okay, so base matching 25 is estimate to the relevance of documents. It belongs to the probabilistic branch of information's retrieval models and improves model based on TF-IDF by adding components that help improve with its limitations. So BM25 models do in fact use TF-IDF, but with two added parameters, K and B. With the help of these two parameters, BM25 can eliminate the bias by normalizing TF based on document length related to the average document, and in our case, the script of the dataset used. Sorry, I have a problem with sharing. Could you hear me?
Yeah.
Sorry, my computer freeze.
I'm very sorry, I don't know. Maybe because it's the different models that I'm loading right now. Okay. Could you see my screen?
Yeah.
Thank you. Sorry for the problems. So here is the result with the query space planets with the models PM25 that we did previously. So as you can see, the model start well with 100% of precision during the 3 first movies retrieve, and after that it slowly starts to converge, having the best precision at 15 at k equal 15, like for 93%, and then it decreased with a precision of 70%. To conclude, the model works well and it's consistent with the retrieving valid movies according to the query that we did earlier with the space planet. And as we said also before, the more precise the queries are and the better the model works. So just we will just make a small demonstration of the best matching 25. So the model is already loaded, and we can the same queries. So you can see that the BM score is going from the 9 to the 6. In general, considered as relevant as most of the movie retrieve is has a nice score and close to each other. And for the process of the coding, the BM25 that we use the library Panda for data manipulations, allowing efficient loading and preprocessing of the movie dataset. We use rank BM25, the library that provides the BM2 150 kp models, essential for creating the ranking of documents based on the relevance towards the user library, like Space Planet we did just before. And each movie script in the dataset is then tokenized and processed into a format suitable for BM25. Then the BM25 models proceed to this tokenize and the corpus of the movie script. Okay, so now let's move on to the BERT model. So we use BERT models, which is a neural network based on the transformer architecture, which use self-attentions mechanism to process text. And what differentiate the BERT model with the others is the ability to read the text bidirectionally. So BERT basically considers the context from the left and the right side of the word, which allows the model, to better understand the meaning and the relevance of each word. So here's the BERT model result from the query love. We first use the BERT model with pre-trained data information. So only the script and the movies that we retrieved earlier with the scraper. So we start with the precision of 0.767 and we decrease when we retrieve almost 12 documents, but in general the value increase until the 13 document retrieve, which leads to a good result from the BERT model result, BERT pre-trained model with the data we used before. So here's the demonstration of the BERT model with the pre-trained script and data we scrapped earlier. So we just load the result with the study. So you can see that the similarity between the solid documents is quite the same. So which leads to a really good result, and calculate with that the precision is good. Okay, so in order to increase this value, we enhance the BERT model. So with one method that we use to enhance the model is to improve the informations of the information that we retrieve. So by fine-tuning the different information that we got earlier. So in order to show you the example that we had, at first, the information that we've got for the pre-trained model was only the title and the script of the movies. And for the enhanced model, we pre-train with the script, the description, and the genre, with fine-tune our CSV data file. So let's see the demonstration about it. Here it is. Okay. I'm sorry. I have to launch it then. Yeah, it just takes some time. And I will just launch with the cloud query. So you can see that the similarity is less than the earlier model. But in general, the similarity is quite good. But the things is that the similarity is less than before, because it could be due to the fine-tuning as we add more information on our CSV file in order to give more details. It can lead to misinformations and bad directions about the informations, which leads to a less precision and also less similarity. But in general, the result is quite good. Thank you for listening. Sorry for all the problems. Yeah. If you have any question. Okay. Have you tried with other queries other than love? Yes, we try space planets too, and also it leads to less similarity from the last model pre-trained with only the description and the script and the title. So yeah, the enhanced model is not as better than the previous one. Yes. So in order to so we before doing the project, we search for different model, and we saw the VSM model, the Vesmatting 25, and we also checked about the BERT model, and we saw that that was the only one who did the bidirectional methods, and we saw that it was really efficient. So that is one of the reason, the biggest reason why we use BERT model. So in order to improve our results and everything. But consider to the other models, yeah, maybe it's not the most successful. Yeah, that's right. Also, we just have a question with Miguel. Could we send you a message later?
So, hi, I will start. So, hi, I will, oh, sorry. So, hi, I will start my presentation. At the beginning, I intended to do the topic 3, but I changed my mind and decided to do the topic 4, which is how to find out the most representative movie order associated with a certain keyword. And I found a useful tool to do this project, which is IMDb+IR, a Python package that allows us to interact with the IMDb database. So there are several steps in the process. We have like 4 steps in our work. First one is search movie by keyword, and the second one is retrieval movie cast, and the third is count actor occurrences, and the last one is identify most representative actor. So for the step 1, we use the IMDb Pi package to search for movie related to a keyword. I make a function. I make a function like search movie by keywords, and this function will create a IMDb instance. So by using this instance, we can search the movie related to the keyword. And in the step 2, we will revise the cast information by defining a revise cast for movie function. By using this function, we also can create an IMDb instance, and using this instance to retrieve movie information by using the movie ID and extract the cast information. And in step 3, we will count the occurrences of each actor across all the movies related to keyword by using the count actor occurrences function. This function will iterate over the cast list and count the number of times each actor appears. And for the last step, we will identify the actor with the highest occurrences count by using the find most representative actor function and this function will identify the actor with the highest occurrence count. I do some runs to get the result. Like, for example, if I take a input like adventure, so the system will use the IMDb Pi package to search every movie related to this keyword adventure, and after that, it will extract the cast information and make a cast dictionary. And after that, it will integrate the cast list and count the occurrences of the account and count the occurrences for each movie of each actor, and last and we find and it will find out the actor who be appear the most to represent appear the most for the related keyword. And this is my work. Thank you. Oh, I because I use the common run to run this system, so I pass the lighting mode and jump to the result. But but I can show you the right now how can it actually work. So like if I take an input as love, yeah, it will take a second to access to the IMDb dataset and uh and find movies and make a actor list and count the occurrences and give the result. Oh, I use the this command line. So wait for me. Sorry. Oh, here. I use the love for the I use the love for the keyword input, and it will use the IMDb Pi package to search a movie and make a actor list. After that, it will count the appearance of each actor in the actor list and will we can get the result. It will take a few seconds to do this process. Oh, okay. Oh, okay. Thank you.